that's the one issue.
There we go, cloud server. And then share screen, this. All right, welcome everyone. My name is Anna Mann-Resnack. I'm a first year in the program in the dev area. Ian, do you want to introduce yourself real quick?
Hi, everyone. I'm Ian. I'm a first year in cognitive neuroscience in Gesture Explains Lab.
Awesome. So Ian and I both have kind of a background in statistics and research. And so we just wanted to share some of our insights because machine learning sounds really scary, but it's really not. And so we just want to kind of break down those barriers. I'm going to set a timer so I know how long I'm talking, which is important. Okay, so this is Intro to Machine Learning. And so this is kind of what we're going to cover basically in this workshop. We're going to address the questions of what is machine learning, specifically talking about the theory, subtypes, common applications. How is machine learning actually done? A lot of this is going to go through Ian's tutorial, but I'm going to go over some of the mathematical frameworks, the familiar statistics that might make it a little more understandable, and then some applications of machine learning in the real world. So current uses, future directions, and best practices. So this is broadly kind of the topics we're going to cover. Really, machine learning is an enormous topic. And so just kind of brushing over the different areas, the basic frameworks and things like that. So first, I wanted to start with the definition of what machine learning is broadly. So this quote, machine learning is an application of artificial intelligence that provides systems the ability to automatically learn and improve from experience without being explicitly programmed. So in that long definition, the things to pick out is that it's models that learn on their own through mathematical concepts. And so machine learning broadly falls under the umbrella of an artificial intelligence. And these are all really closely related to statistical science. So the first thing I want to talk about is something more familiar to us, statistical learning. So in the broad sense, statistical learning refers to a mathematical perspective on modeling data with a focus on data models and on goodness of fit. Machine learning is not so different, except that it's a computer science perspective on modeling with a focus on algorithmic methods and model skill. So the biggest difference between that, statistics is really focused on, is this predicting what we're looking at? Is it accurate? Where machine learning is a little more focused on the methods and how well the model performs. But there's a lot of similarities. And so some of the language is really just about translation. So in statistics, we might call something a model. In machine learning, you might call it networks or graphs. Parameters and stats is weights in machine learning. Fitting and stats is learning in machine learning. Test set performance is generalization. And then we have different types of classification or clustering that's really just supervised and unsupervised models in machine learning. And so this slide is really just to bring in the idea that machine learning isn't that different from stats. It's just the automated process. And one of the reasons it feels so inaccessible from statisticians and behavioral scientists is that there's a lot of gatekeeping language. Like most academia, it's important to break down these barriers and realize that they're not so different. So I wanted to start off by first talking about neural networks and deep learning, because I want to give you a broad scope of the framework for how these things work. So on the left, we have a simple neural network, and on the right, we have a deep learning network. And you may notice the main difference between the two is these hidden layers that are called, hidden layers, and they're made up of neurons. This is where neural networks, if you've never heard this, gets their name, because these nodes or neurons actually act as thresholds for information, much like neurons in our brains do. So when you're inputting information, it's bypassing through all of these different nodes and neurons, and it has to pass a certain threshold in order to go on to the next step or to determine what that actually is. And so in a simple neural network, you just have this array of neurons, and it's deciding based on the value what it should be categorized as. And you get an output that tells you it's this or it's that. In a deep learning network, you have a couple layers. And so you're not just passing through one hidden network, but multiple. And therefore, the decisions made are a little more complex, and they're also going to be higher in power. And so this is just the broad framework of the decision-making tree of a neural network or a simple neural network. And so there's neural networks in machine learning, and then there's what they call classic machine learning. Within machine learning, you have two main types of models. You have unsupervised and supervised machine learning models. Supervised models work in a specific way in which you have a trained data set. So if you look to your left, you see step one. Its label is cats. And so you train and set the parameters that if it looks like this and it meets these requirements, that thing is a cat. And you feed it into the machine, and that's called a training set. In step two, you can see that you introduce new data. So you have cats and then you have dogs. And so the model is trained to know what is a cat. So even if you bring in new images of cats, it'll still label that as cat. And everything else is just not cats. And so this kind of machine learning can be really good for like bivariate regressions, classification, where you're really just looking, is it this thing or is it not? And so when you're trying to find groups or just like split your samples in two, you can just look at, is it this or is it not? And that works off of a trained dating set. There's another common model, like I said, unsupervised machine learning. And this is one of the more complex models in which you really see the power of what machine learning can do. And so in step one, in this case, there is no training set. You just input a bunch of data, and the machine itself, the model, picks out the distinguishing features and creates groups based on similarity. So within those hidden layers, it decides what is most common between these different stimuli, these different data points, and it groups them based on those factors. So you have similar group 1 and similar group 2. And so the main difference between these two models is that in the first group, you know what one group is. You know it's cats because you've labeled that based on your training data. However, in this kind of model, and unsupervised, you have to be able to interpret those results and understand what the common factors actually lead to. So in this one, you can see that the first group, similar group 1, is cats, similar group 2 is dogs. But if this were a training data set, maybe splitting on depression rates, you would need to understand which group represents non-depressed and which group represents like depressed patients. And so one of the main things that also differs, but is similar to psychology or statistical psychology, is like the idea of setting parameters. And one of the really good applications of machine learning is that you can either do this, if you can see at the top, machine learning broadly in those supervised and unsupervised models. Specifically in this example, the top is showing a supervised model where you're looking at features, you're defining them, the model classifies, and it gives you the output car, not car. The deep learning is showing more of an unsupervised model, and where you just input data and there's feature extraction, classification, all within the model. You don't define anything, but it still tells you the output. And so this is one of the confusing things about machine learning, because they want to divide things, but they're really the same. So machine learning and deep learning, neural networks, and different types of models can often mean the same thing. So like in these last couple examples, I've shown you what neural networks look like, what models look like, but often they're used interchangeably. And so that's something to consider when you're reading through the literature, that a lot of times you have to dig deeper to realize what they really mean. And so this is just a very helpful visualization of the different types of applications for different types of machine learning. So you can see that overall, all of these things fall under the umbrella of machine learning. And then you have unsupervised learning and supervised learning, which we just covered, which is going to be one of the most common applications. You also have reinforcement learning, which is really a little bit more common in like building robots or detection tasks, things like that. Reinforcement learning sounds very familiar to us as psychologists because that's something we study in theory. And machine learning just means a little bit different. It's based on performance. And so it's not going to be used as common. So specifically in unsupervised learning, this is really good for dimensionality reduction. So if you have a huge data set and you don't really know where things line up and what things match, unsupervised learning can be very helpful for that because it finds the structure in the data itself. It can also cluster things based off of that. And so if you're looking for groups, this is really good for like factor analyses. If you're trying to build a questionnaire or if you're looking at a large group. Then you have supervised learning, really good for classification. If you ever do any kind of studies looking at images, if you're looking at specific features of an image, I know there's a big body of work that looks at emotionality in the face and determining what emotion is being displayed through machine learning. There's also regression, so you can do predictive modeling. You add in a small set of trained data. This is what I do in my lab. We train a small amount of human annotated data, and then we apply that to our larger data set so that it predicts all of the work that we do normally through human annotations, and it saves us a bunch of time. So that was a lot of intense models and frameworks and stats talk. And so I want to switch gears a little bit and talk about what machine learning looks like in the real world. So a lot of us have heard of Cambridge Analytica. This group is largely blamed for a lot of political sway in the last election. And I want to talk a little bit about how they did that. So I believe it was 2015, Cambridge Analytica actually stole, or it was leaked, a model from a paper that was written from Cambridge. And so in this original paper, they took about 50,000 Facebook profiles and they looked to see if Facebook activity actually predicted real life things about people, like their political affiliations, religious beliefs. And they found with a high degree of accuracy that they could predict those things. So based on your likes and how you interacted with Facebook, they could tell a lot of intimate details about yourself. And they called this a psychographic profile. And Cambridge Analytica took it one step further, where they actually took Facebook's data and made millions of psychographic profiles. And what they looked for specifically was not just, can we predict your religious affiliation, political religious affiliations and beliefs, but can we tell your big 5 personality traits and which people will be most susceptible to persuasion. And so that's what they did. They aimed ads at people who were more persuasive based on this data with a high degree of accuracy. And now the reason they were so successful is because Facebook's data is squeaky clean. If you've ever worked with behavioral data, you know that it takes an incredible amount of data prep just to look at what you're trying to see. And so in this case, the opportune data set was available in which the data was squeaky clean, it was easy to process, it was easy to work through. But you'll see that that's not always the case. So machine learning is also used for a lot of good. And a lot of people are saying machine learning can revolutionize the healthcare industry. It can change lives. And that's true. The problem is, unlike Facebook, medical data is very messy because it's records, not reports. And so people are trying to create clinical decision support tools, CDS. And these are tools that doctors use, and they're not new, but they're tools that doctors use to help to determine what a diagnosis should be, how effective a treatment plan may be, what the mortality rate is expected to be in a hospital environment, all these different factors that go into actually being a medical professional. And we want to use machine learning so that those predictions are better, so that the diagnostics are better and the treatment plans are the most efficacious. But the problem is the data that that's pulling from is not very clean. And so when you're thinking about machine learning, you're thinking about how can this be used in the real world? Understand the limitations that come with that on if the data is messy, it's going to take a lot of work to get it to a clean place to actually have a good model that works. And so this is just one of those examples of like, sometimes it's really easy to do not great things depending on what data is available to you. And some of the things that we really want to do are a little bit harder because we have to think about what records we're pulling from. So I found this really good paper kind of tying in what psychology and machine learning would look like, how it can help psychologists, and what are the things that we should consider. So the first thing is that machine learning models are largely agnostic. So when we are looking at data, we set parameters beforehand on this score means this, and this result means this. And so when we're running our model, we innately create a bias for that model. Machine learning, especially in unsupervised models, does not care what your score means. It is looking for patterns that are real and that are present and differences that are a little more accurate to believe. And so that's one of the benefits of machine learning model in psychology is that it takes the human factor out of the human behavior analysis. And so you can look at things with a little bit of a clearer lens. However, there is some things to consider. So they call this the interpretability accuracy trade-off. You'll find that better performing models are harder to interpret. Why is this? So in a supervised model, you are creating a training set and you know what those parameters mean. And so therefore, when the data comes out, you know, this fits and this doesn't, or this is my group and this isn't. However, in one of those more advanced models, a deeper learning network and unsupervised models, these might have more power and they might be more accurate, but they're more difficult to interpret. And so you have to consider the interpretability accuracy trade-off. And actually, this paper has some really good suggestions for using different models for different parts of your data process. So for like feature extraction, maybe use an unsupervised model, but for checking the data, use a supervised model based on that data that it gives. And so it gives you some tips and tricks for understanding that not one model fits all. And it's important to realize the time considerations, the checks you need on your data, and just realizing where that trade-off is going to come into play. Another way that psychology and machine learning can really benefit is that machine learning is much better at cross-validation and it avoids overfitting. And so one of the things that psychology and our field is facing as a whole is we're still talking about this replication crisis. And one of the things that happens is that replication crisis often occurs due to the fact that most models are overfit, meaning that the analyses done on that set of data are too closely related and therefore aren't generalizable to that same replication in a different lab with a slightly different design with a different sample. And so machine learning allows for more tools so that you can do cross-validation, that you can run models again, you can validate them in your own data set by leaving parts out and then bringing it back in, making sure that results are generalizable. It just has a lot more tools built in so that you can try to get more accurate readings based on what you had. And so next we're going to go on to Ian's breakdown, but I wanted to stop for a second and ask if there are any questions so far or if I can clarify any points that I've made at this point.
I have a question. Are there models that deal better than others with like noisier data, or I'm thinking like smaller data sets, right? Like how power hungry are some of these models? And are there some, I'm assuming that there are some that are better at handling that, like a smaller, noisier data set?
Yeah, so there's this common trade-off where when you have more input than subjects, machine learning is a better option because it's better at finding those patterns within subjects. If you have more subjects than like those inputs you're looking at, it's better just to use traditional statistics. And so in this paper that I cited, that I included in that last slide, it brings in a lot of great examples of which model is best for what. So a lot of people will throw around random forest, which is all about like finding these connections and things like that. But is it better for noisier data? That's something that you have to look at and decide, because like if you look at something like MRI data or fMRI data, it's very noisy. And so we do a ton of cleaning beforehand, but then when you get to the endpoint, there's still thousands and thousands of data points. And so it's one of those things where it's like, is it oversampling? Are we too sensitive? Is it data too clean? And so there's this noise to effect ratio that really has to be examined for every kind of model. And Ian's going to talk about some of those things that you can do to check if your model is actually performing the way it should, or if it's overcorrecting or undercorrecting. There's all these little ways that you can check to see if your model is actually benefiting you or if it's showing you an effect that's not really there. But yeah, there are definitely like models you can pick that are more appropriate for each kind of data set that you're working with.
Cool, yeah. Thanks.
Any other questions at this point? If not, we'll move on to the tutorial. Cool. Ian, go ahead, take it away.
Awesome. So yeah, that actually was a perfect question to lead into the tutorial because I actually chose a model that draws upon a method that is designed for the purpose of generating more robust predictions from a model. So I'm just gonna share my browser. So if I share this screen, I should be able to hit present. Is that correct? Does everybody see the PowerPoint? Okay.
Yeah, it's perfect, Ian.
Great, thanks. Okay, so I'll just skip through to where we were. And yeah, I'm actually gonna just, this paper reminded me of another paper that I read that ran a simulation study that showed that if you just, they put, the only thing that they modulated in this simulation was the reliability of the predictor variables of some outcome. So they generated data from a regular regression, but they, in a continuous fashion, just kind of amped up or decreased the reliability of those input variables by just introducing some noise, and it very quickly, I remember their point showed that it very quickly resulted in less accurate predictions for the response variable. So definitely the amount of noise can really hinder these machine learning methods that were designed to model the actual behaviors of an individual on Amazon or something like that in many cases, or in some cases just actually things from the so-called hard sciences that are much less subject to noise. So several methods have been, I'll skip over this for a second, just that several machine learning methods have been introduced to deal with these problems that we face in the behavioral sciences or the social sciences. And one of them might be bagging bootstrap aggregation, which is a common method where instead of fitting one model to your data, you fit the same model, say 1,000 times, but each time you resample from your data with replacement. So some individuals might be in that sample that you're fitting your model to 2 or 3 times. Other people will be left out, and so the areas where subjects demonstrate the most heterogeneity, that kind of will get amplified, whereas the effect of outliers will sort of be attenuated as a result, and that's called bootstrap aggregation. And you could bootstrap and aggregate 1,000, linear regressions. So that's just one resampling strategy. So what we're going to talk about today is boosting, however. So boosting, like bagging, is an ensemble method where you are fitting multiple models, and they're usually all the same model, the same base learner, it's called. And each one, though, is going to be sort of prevented in itself from overfitting. So say each one's going to be a decision tree. We're going to say, fit the decision tree to predict our outcome. Say we're interested in, does a person have diabetes, yes or no? So it's just a binomial response variable, and we're gonna build 1,000 models to solve this problem. If you use boosting, you can say each tree will only allow it to split one time. So we have several input variables, features, say they're like blood pressure, insulin would probably be a giveaway variable, but other things like that, age, something like that. And we'll say each model will just be able to split older than 60 or younger than 60. Blood pressure above, I don't really know what the threshold is for that variable, but you get the point. And so each model is actually going to be somewhat inaccurate. But what happens, and this is proven through statistical theory, and simulation studies also have proven these methods. The committee will end up making a better prediction than any of the individual models. Of course, and I guess the reason being that one individual model may be, really actually highly accurate, but sort of overfit to the majority of the cases in the group. And so after averaging everything, you end up with with a solution that is more better able to generalize to a different sample. So with resampling and for solving the issues of dealing with a lot of noise, it's not really to say that we're going to find a model that better fits our sample. The purpose is that we want to build a model that is closer to the ground truth, even if our sample is a little bit noisy or has some outliers with respect to the population. The population, of course, we don't really know. We haven't really sampled them perfectly. So that's the idea behind boosting. And right, you can actually build any type of base learner with boosting. It's just the name of the resampling method. Okay, now I'll jump back to what we're going to go over in the actual, let's switch over to the code. I see the time's ticking away here. So what we're going to do is we're going to go through pretty much the whole pipeline, and some of the things that Anna was suggesting will be important here. So we're going to read in the data. We're going to split it into the training and the test sets. We're going to make sure, we're going to take a look at the data, make sure everything read in as expected, that there's no missing data. You should definitely do that more extensively on your own. For this tutorial, we happen to read in a data set that is extremely clean already, provided to us for that reason. So I'm just going to share now the other screen. Okay, so hopefully we all see some code here. Okay, great. So, all right, so let's get to it. So say you have some response variable you want to predict. It could be anything like I said, do one of your groups, do one of your participants have a particular diagnosis? Obviously not one sample at a time, but you could do that as well. Build a model to just identify one individual. Something used for fingerprinting, for example, connectome-based fingerprinting, or other types of things like that. Anyway, so that's analogous to the type of data we're going to be working with in this tutorial. Oh, I'm sorry, we're doing a different one. So we're actually reading in a data set that has the ratings of different wines. So there's red wine and white wine. We're going to read in both of these files, and they have a response variable where people have rated the quality of this wine. And we're just going to concat. Yeah.
Ian, is this code available for people to download right now and try to follow along with you?
Oh, yes. I totally forgot that. Thank you for reminding me.
You can drop the URL in the chat if you like.
Okay, yeah, cool. So here's the link to, it's on GitHub, so there'll be a little bit of necessity to know how to use GitHub. But this repository is a public repository that I made that has actually several tutorials on it. So the one that we're going through today is this code right here, GBM regression. So like the code we were just looking at is right here. It's just formatted as an R Markdown file. So it has like these little code chunks here, they're called, and they're separated by these 3 backticks. You can open this file, a .rmd file, directly in RStudio, and it'll look exactly, it'll look more like this, not exactly, but you'll see the code and those 3 like backticks around every like section of code will be there. So if you want to download this, you can literally copy and paste. This is all our code, essentially. You can copy and paste it, or you can go directly to the link that I put in the chat to the repository itself. You can download that by just going here for clicking to download the code, in which case you'll actually be downloading a zip file that has all of this code. There's 2 other tutorials in here just about plotting in R. You can delete those, you can use those, whatever you want to do. Be my guest. And the one that that you would open today is this one right here, gbmregression.rmd. So if people want to run that right now, I'll actually go ahead and try and do that. You can just tune me out for a bit. I'll just give you a little bit of background about the data set. And hopefully we'll be all caught up for when I go through the actual computations. Okay, so so we're going to build a gradient boosted machine to predict the human generated quality of the wine. So these are two data sets that they have different qualities rated, or sorry, they have quality rated, and then they have different components like features of the wine. And so we can see them here. So I'll just go right ahead and start with the actual code. So hopefully everybody has had a chance to download that stuff. So these packages are the ones that we'll be using, by the way. And then this is just later we generate plots, and you can set a theme for every plot that prints out in this file will adopt this theme. So that's all that this is doing. Again, this is just reading in the packages that we need to do the computations down here. And this is an inbuilt function in R. The data is provided to us by the University of California at Irvine. They have a whole bunch of these data sets, and you can just download them somewhere on your computer. I use a relative path so that you could run this directly. Just so you know, it will be in your home folder there. Okay, so we read in the data and we're just stacking the two data sets. So we just have the red wine and the white wine, and we're just stacking them up together to make one big wine data set with all the wine. And we use the structure function to check out what the variables are in our data. So we have the different chemical components of the wine, and then the last variable here, this is our response variable. People have rated these wines on a scale from, it looks like 3 to 9 are the, probably 1 to 10, but it looks like there are only ratings of 3 to 9, representing the, quality of the wine. So, oh, and if there are any questions, just feel free to interrupt me. I actually don't see the chat anywhere. So maybe if there's a question in the chat, Anna, you could just let me know as well.
I got you.
Thank you. All right, awesome. So moving right along here, we want to split the data like first and foremost. So this is a key component of machine learning. Again, like nothing really about these methods are magic. Well, there's some things that are pretty wild, but they're all based on statistical theory. What we're doing is just methodologically very principled. So here we're not going to use all the data we have. Obviously, if you have a really small sample, this is difficult. But there are ways around it, such as bagging and boosting, which is what we're going to be going through further down here. But for now, we have the luxury of like 1,000 of these wines are rated, so we can just partition the data right off the bat into a train and a test set. So what we do with that is we fit the model to the train data, and then we predict based on the test data what their predicted values would be from the model that we fit. And that's how we really assess how well our model performs. Okay, so let's see. We just use base R functions for that. So we're just doing sample. This is going to resolve to a vector of row indices for the train data. So when we do sample, we're just selecting a random 80% of that data, and the rest we're just going to throw right into the test set, as we can see right there. So now we've got our data set up. I also saved this out. We're also going to repeat this pipeline in Python, so so we can access it now on our computer to do that later. Okay, just looking at the time here, I'm probably going to have to go a little bit faster. So I'm not going to be able to explain everything, but basically, if you're familiar with formulas in R, you'll recognize this, that we have a response variable and a tilde, and then the dot just means predict our response variable from everything. And we're just using the GBM function from the GBM package to fit our gradient boosted machine. The distribution here we set to Gaussian because we have a continuous response variable. And what the gradient boosted machine function does is it builds n dot trees, number of trees. And those are our base learners that we were talking about before. Another important component of the gradient boosting algorithm that's slightly different from just regular boosting is that each time each sequential tree is actually fit to predict the residuals from the previous one. And so in that way, we are actually always just incrementally improving our model by fitting to just those subjects or just those rows that were really hard to predict in the previous tree. And so that's why this is a particularly advantageous model to use when you have, minority of cases that of people with a rare disease that you need to predict, or just a lot of outliers, but outliers that you don't want to just average out, but that you really are focusing on. Boosting can be real, in particular, gradient boosted machines can be really helpful. So shrinkage is the term for what I was just describing. So each time the previous tree generates residuals, it gets multiplied by the shrinkage factor. And that's like usually in machine learning, they'll call that the learning rate or the step or the jump along the gradient. That's why it's called a gradient boosted machine. So basically, in a nutshell, and so that you don't get tripped up with this in the future, when you compute the residuals, you're basically seeing where the model is performing the worst, essentially. So that creates kind of a gradient in a way. It's just like sort of a way to look at it. But you're basically progressing along the gradient each time that you fit your next model to the residuals. But you don't want to get sort of, so if you don't use the shrinkage, what happens is you could end up finding a local minima or maxima in that gradient function, and then you have overfit essentially, which is what we're trying to avoid. So that's what the shrinkage is used for. And then the bag fraction is another important thing that helps you prevent overfitting essentially. And I'm going to just skip over that one because that's applicable to bagging and many other types of models, not specific to gradient boosting. So just in the service of time, we'll keep going here. So we fit our model, and as we can see, the black line is the error rate in predicting the squared error loss in predicting the quality of the wine. So as we can see, as we add more trees, so these iterations are adding another model each time fit to the residuals of the previous, we're obviously decreasing the error each time. But the green line here is the cross-validation error. And as you can see, it's a little bit higher. So if you just fit a model with any of your data, a linear regression, a logistic regression, anything that you want to fit, you're fitting this black line every time. And we can't reproduce this even with cross-validation folds in the same data. So that's kind of just showing us that it's really important to use cross-validation to try and evaluate our models, and that I think will solve a lot of the reproducibility crisis right there. Okay, so now what we really need to do though is we need to generate our predictions for the test set so that we can score the model with respect to those rows that we partitioned off into the test to really get a sense of how well does this model perform on data that the model has never seen, not even in any of the cross-validation folds that we did within the model fitting. And in that circumstance, we explained 34% of the variance in our never before seen data. So this is an R squared of 0.34. So that's all this code is doing right here. With gradient boosted machines, you have to you get to use these built-in functions from the package that will tell you which was the best iteration. We see it was here. And then just with that information, I just like, drew out a little data frame so that it prints out all pretty like that. But all we're doing is we're throwing the predicted values. We're just saying predict from this model. We're giving it the test data. And we're saying predict from the iteration that we found to be the best one. Give us those predicted values compared to the true value from the test data. And we'll compute the R squared. And this is just a function that we imported above with the other packages. Same thing here. Okay, so let's compare it to a linear regression. Same deal. I took the train data, fit a linear model, and you can do cross-validation. With the linear model, you can do any of these methods with regular parametric models. And doing so, we only explain 28% of the variance. So yeah, so as we can see, just by doing things like boosting, or in this particular case, we also fit a regression tree that may have helped us. But those trees that we fit at each iteration were by default, they only had like 1 or 2 splits in them. So really, I think what this shows us is that just by doing boosting, we can improve the predictions of a linear regression. So I'm going to jump ahead to, there's actually a lot more to go through. So I'm going to go through the computing variable importance really fast, because I want to leave time for questions at the end. And then we probably won't get to the Python code, but I'll go through this because this is an important concept. That basically another thing in machine learning that we can do is that we can use sort of like many iterations of the same thing. We have a lot stronger computers nowadays than we used to in the past. So one thing, instead of relying upon parametric models to generate our sense of what is the effect of one variable on our accuracy or on the response variable itself, we can also take these variables out of the model one by one and calculate to what degree the predictions of the model change and to what extent does the model overall become less accurate. And that is actually, research has shown that this is a good indicator of what's a good variable overall. So doing that like 100 times with every variable. So you basically generate those predictions. So like what we were doing up here, it would be like putting this into a for loop. It's actually really simple. Put this into a for loop. Each time you just permute one variable from the predictor variables in the test set, regenerate your prediction, your R squared. It's going to go probably down because now you replaced one of the variables with noise. But for some variables, it'll go down even more. And we can say that that variable was really important for the overall performance of the model. And then we divide that by the actual performance of the model. And we see this one here, for example. Oh, of course. So alcohol was decreased. So if you take the alcohol variable and you just replace it with random noise, the prediction accuracy of the ratings of the quality of the wine changes by 46%. So we can interpret relative to something like the volatile acidity. If we take that variable out, we replace it with noise. Judges' ratings, our ability to estimate judges' ratings go down by 15%. So yeah, these are like the scaling factors. So this would be like 1%, 15%, 2%, 6%. This one didn't change at all. Same with that one. So yeah, and you can plot these. Here's code for plotting them. Yeah, so I feel like I would like to go through a lot more of this, but we probably don't have time to go through all of it. So I'll just jump down to here is there's elements of the models that you can tune. So I'll just give you the high level explanation so that you can take a look at this stuff, or at least you'll have a sense when you need to build out, 100 trees. So things like that, those are called hyperparameters, and they can all be kind of tuned, or basically you set them beforehand and you can evaluate, just like we do with the variable importances, we can also evaluate how it changes the performance of the model. So that's called tuning, and this package just does it for us. So that's really great. You just have to know, what are the parameters, what is the range? Like if you put like 100 here, it'll probably say there's not 100 splits to make error or something like that. And we just get the same kind of outputs. So here the shrinkage was 0.1, the interaction depth was 1, number of minimum observations in a terminal node for the tree was 5, and here's the corresponding performance of the model. We can see that the best performing model actually is here with these particular settings, and then this is now our final model that we would then deploy to the next round, or we would then validate this with the test data. And that's what we do here. Caret also, sorry, this is being run in the Caret package. They have some really great functions for doing like any kind of machine learning problem you have. Probably Caret has coded it already. And so they also have in the outputs the best iteration, and we can print out what we were just seeing up there. And we can extract the best model, and we can even take that model and throw it through these functions here to get these plots for variable importance. So yeah, very convenient. So in 1 minute, I'll just say that we can do the whole thing with Python. And if you are more comfortable with Python, or you just want to learn it because it's good to know. It's a very versatile language, and a lot of jobs will be interested in candidates who can code in Python. This is how to do the entire pipeline in Python. So you read in that data set. This is the only part that's different because we wrote this CSV out earlier after we read in the 2 data sets. And so we read it back in, same variables, just as we were expecting. Okay. Splitting the data just as we did before. Instead of Caret in Python, we use sklearn, and it does everything exactly that Caret does. We set up the different tuning parameters that we're gonna try out different values for. We fit our tune. We say for each of these different combinations of tuning parameters, estimate our outcome with a gradient boosted machine. Also, a function from sklearn. Another function from sklearn is the grid search CV function. And in here, we just throw our estimator, our model, our gradient boosted machine, and the parameters we want to try out. Just throw them right in here. Say we'll evaluate each one using 5-fold cross-validation, and we get our results just like we did with Caret. It printed out all of the results here, and we have the best parameters. It tells us best parameters, and now it gives us the final estimator is, oh yeah, right. You don't need to extract the final model for sklearn, and sklearn also has the, oh here it is, best estimator, has the ability to just generate these permutation variable importances, and we get the same results. So yeah, the most significant variables are pretty consistent between the 2 methods. So I'm going to stop sharing now. And I see there's a question in the chat. Cool plot, definitely. Yeah, the plots are pretty cool. And that code, a lot of the plotting codes, like I think those packages generate them for you. So, yep.
I just want to add some, we threw a ton of information at you guys, and I think the biggest takeaways are that a lot of this is building on information that you already understand, maybe just rephrased in a different way. And coding is just intuitive Googling. So Ian and I will both tell you that the majority of our R scripts and our Python coding really comes from reading other people's examples, understanding what might work, and that machine learning is not inaccessible. It is, you don't need a computer science degree. I never took one computer class in my entire life, and this is how I do my coding. A lot of it is from the charity of very nice individuals who will sit and explain and hold my hand through different concepts. But it really can make psychology and behavioral research better to understand how to use these really powerful machines to our benefit. And so just understand that, like, you know, it's all building on things that we already know. It's just learning how to apply them. And it's okay to like ask for help and realize how to make your research better. And so do we have any specific questions? If anyone has some ideas on like, would this work in machine learning? We'd be happy to talk about them with you just for the next couple minutes.
I have a question, maybe just like for my own, like trying to like put things in more of a like, I don't know, traditional statistics that I'm used to. So this like permutation, or yeah, it's a permutation one where it gives you like the best performing variables. Is that right? So like in my mind, that's like analogous to like a stepwise regression, but maybe it's not shitty and it doesn't overfit.
Yeah, exactly.
Yes.
So is that okay? And then like I forget what it's called already, but the other one you talked about, what's it called? Like, it's like bootstrapping.
Oh, boosting.
Boosting, yeah. So is that right, that it's pretty much just like bootstrapping, except instead of doing with replacement, you're like just splitting, or basically just taking like subsets of the data? Like,
Yeah, exactly.
are they random subsets of the data, or like you define the splits?
Yeah.
Maybe you said this and I missed it.
Yep. No, that's right. So actually the key thing with boosting is usually that you'll build a model that's like flexible. So the you want to use like a decision tree that you can constrain that model, and you can say, you know, don't like build it. So the big difference with like bagging, bootstrapping is for decision trees is that in a random forest, you'll build out the entire tree. So you'll predict the terminal leaf for every single subject. But in boosting, you'll just prevent it from doing that. Each tree will be a little bit more inaccurate than a random forest itself. Than each tree in a random forest. But then you aggregate it, and in aggregating it, it works out.
Cool. Well, thanks. So like this was a really good introduction.
Yeah, and the biggest thing that I wanted to get across is like a lot of the gatekeeping comes from they switch the language ever so slightly. So, you know, and just really understanding, thank you, Pelin. And just like understanding that it can just save you so much time. I never thought I would go into coding because I was like, I'm going to be a psychologist. I don't need to know any of this. I just need to know SPSS. But like in my lab, just our data set alone is over 2 terabytes. You know, like going through that from a human level is just inaccessible. It slows down our science. And so like the way we use it is that we do like a subset of annotation. So we do training models. And sometimes what we do is we'll create training models and then lead into unsupervised models so that the prediction is better and better and better. And my lab has the benefit of 2 of our grad students are actually electrical engineers. Thank you, Nick. And it just, you know, really takes reaching out for those resources to understand like how they can help your lab and how they can just make your science so much easier on your standpoint. And really understanding that like we as psychologists like deserve to be in machine learning. We deserve to be in this field. And yeah, just breaking down those barriers is really, really important. Realizing that we could be coders just like computer scientists.
On that note, another great resource for like anybody who's interested in like why things work and like what they're doing behind the scenes, elements of statistical learning. and that's a textbook, and Intro to Statistical Learning.
Mhm.
And those are both like textbooks that will have a lot of R code like in them. And yeah, they like show you like the summation notation of like adding predictions from a million models and like why it's actually reduces the mean squared error and things like that. So if you do prefer to see things in the terms that we're used to, those are great resources as well.
Also, Coursera is where I learned most of my coding. If you literally just write them a paragraph of like, I'm a poor grad student, they will give you the class for free, no questions asked. I have several classes from the University of Michigan that I have not paid a cent for that I can access whenever I feel like. And so like the resources are out. And also like I bother my lab mates and the engineers on my team constantly. I'm like, a for loop should do this right.